Welcome to this video. A couple of things today I want to talk about that have got tremendous long-term significance for where we go with this pandemic, and indeed where we go with other future pandemics as well. Now, the first one is on the British government has authorised human trials. Human beings will now be deliberately infected with the virus, vaccinated, and we'll be looking at the studies that can come from that. So that's a bit of a landmark. It's the first time it has officially happened in the world with SARS coronavirus 2. And the second one is from the Journal of the American Medical Association, looking at herd immunity, and again telling us where we're likely to be in a year or two's time. And the bottom line is, I think the data is pointing to a good outcome in 2 or 3 years' time, that this pandemic will stop, and that I believe that SARS coronavirus 2 can disappear. Now, that's still being debated, but that's still my current position. But anyway, let's get straight on to the detail now, the British government's position on human challenge trials. So this has come straight from the UK government website, just cut and pasted it. Expert partnership to explore and establish human challenge studies of COVID-19 in the UK. Now, the background here is that all the trials that have been done so far and all the studies that have been done so far on this virus are people that have been naturally infected. Here, people are going to be deliberately infected, so they can be studied prospectively in much more detail. And as well as that, all the phase 3 clinical trials that are currently ongoing into the vaccine, people are vaccinated and told to carry on avoiding the disease if they can. A few of them will become infected, and we have to see if those few that become infected are going to enjoy immunity. So it's a very natural process, and it takes a long time as we wait for people to become naturally infected to see if the vaccine works. This cuts all that short. It means it can be done so much quicker. So this is directly from the government website. Government investment will back the studies in partnership with the Imperial College London, this organisation, I think this is a commercial organisation here, and the Royal Free Hospital in London. So that is all from the government website. Check it out for yourself, you can read about it all. And again, this is from the government website. New research will explore the potential for new studies to accelerate development of the whole thing. Accelerate the development of our study of the nature of infection and the evolution of the illness and the development of vaccines. So let's go on to look at some of the things it's saying. A vaccine candidate that is proven safe in clinical trials. So the vaccine candidates that are going to be tried in these people that are going to be deliberately infected is one which has already been studied to a large degree and is deemed to be safe for human use. So that is encouraging. Carefully select healthy adult volunteers. 90 people are to begin with, aged 18 to 30. 90 doesn't sound like a lot, but given that there's an awful lot of data to be collected on these people, that's actually one heck of a big research project, because there'll be so much information to collect on them on an ongoing basis, and tests will need to be done on an ongoing basis, and indeed they will need to be followed up over a year to make sure there's no long-term complications of the vaccine or being inoculated with the SARS coronavirus 2. And I must say, I have to admire what these people are doing. This is a noble thing to do. There's an element of risk for themselves, of course, and they're doing that for other people. So we can only applaud that. It's a great thing that these people are volunteering to do. So they're exposed to the virus in a safe and controlled environment. Well, the environment is certainly controlled. It's never completely safe, of course. So the government's not quite right saying it's completely safe. It's as safe as it can be made. But that's never completely safe. There is not many guarantees in this life, and this certainly isn't one of them. But risks have been minimised. So that's good. Closely monitored effects on the volunteers 24/7. They're going to be really closely watched. See exactly how vaccines work. So they'll be able to study the blood and the physiological response to the vaccine as it takes effects. That'll identify side effects. And the other thing is they're going to be given a controlled dose of the virus. These are called virus characterisation studies. So just how much of the virus does it take to cause infection? Is it 100 viral particles, 200 viral particles, 500 viral particles? And how is the viral dose that these people will be given, the inoculum, how does that relate to the severity of the illness? So this group here, I'm not quite sure what this stands for actually, but this group here, this one, I think what they're doing is they are actually supplying the live virus. So they must be culturing the live virus and supplying it in known doses so that the clinicians can give a precise known dose of virus to these volunteers to see what the effects of that are. And we would expect that the lower dose would cause a milder clinical course. That's what happens in influenza, so we expect that's what's going to happen in COVID-19. That's why we're wearing masks, to lower the inoculum dose. So that can be done. These are called virus characterisation studies. Discover the smallest amount of virus it takes to cause infection. Good. Accelerate the vaccine development, massively so, because we're not waiting for people to be infected. We know they're already infected. Or we can vaccinate prior to infection and know that these people have been vaccinated and then know the effects of the virus and the vaccine really very quickly, greatly accelerating vaccine development. So this is just good all round. It means all this data can be collected, and it is that there's a very specialised, highly skilled team that are doing this. It's going to be monitored for up to a year afterwards, which is good, potentially saving so many thousands of lives because of the accelerated nature of the programme. We'll get information quicker. Now, we know that you and I do suspect that human challenge studies have been done in other countries, but it's never been admitted or published before. This is all up front, it's all prospective, it's all in controlled circumstances, it's 100% above board, definitely completely volunteer people. Whether it's been done in other countries or not, you and I will probably never find out. We have our suspicions, but this is the time that we're going to get good quality data. There's going to be controlled entrance to the facility at the Royal Free Hospital, decontamination of waste. There's going to be dedicated laboratories for carrying out tests, so the quality of the tests will be good and they'll all be done at once. All the air leaving the unit is cleaned, so that's good, so we're not going to infect those around us. Now, this has already been done with malaria, typhoid, cholera, norovirus and influenza viruses. These human challenge studies have been done before. So it's not entirely new. And of course, there's many stories in the history of medicine. John Hunter, for example, deliberately infected himself with syphilis when he was studying syphilis and gonorrhea. James Phipps was infected by Edward Jenner, the first person to be infected with cowpox that produced immunity to smallpox. Robert Koch, the father of microbiology, he infected himself on occasion. John Hunter, by the way, is often described as the father of modern surgery. He was actually the teacher of Edward Jenner, who inoculated James Phipps. Of course, Barry Marshall in recent times. Barry Marshall and his colleagues suspected that peptic ulceration was caused by Helicobacter pylori bacteria. So Barry Marshall deliberately infected himself with Helicobacter pylori, developed the gastritis, developed the ulceration, and was able to treat himself, thankfully, with antibiotics and various other things. But the downside, so we've got a history of this. This has been done by noble people in the past. Unfortunately, it's not starting till January. It takes time to organise these things. First results in May 2021. Not an overnight thing, but potentially a complete game changer, actually. So, yeah, good one. And our admiration and thanks to the people that are taking part. Now, just a quick revision of herd immunity. We do know this, we've done this before, but here's a person who's actively infected. And these people, I, that stands for immune, these are immune. The S are susceptible people. So the susceptible people here in this crowd, but the actively infected person is not in contact with those directly, and these people here that are immune can't pass the virus on. So this is a situation of herd immunity, which is what we want. So the active infection, the actively infected person only comes into contact with immune people, and they're not going to spread it onto the susceptible person or that susceptible person. However, in the non-herd immunity situation, here we have the person with active infection, and we see that they are in contact with the susceptible person, and they can pass it on, as he can pass it on and she can pass it on. So that's a situation where we do not have herd immunity. Now this person here can't pass it to that person there because that person's immune. So the infection can't go from that person to that person to that person, but of course it can go from that person directly to that person. So that is the herd immunity situation, as we've looked at before, and that's the non-herd immunity situation. So this is what we're talking about in basic terms. So this is a fairly interesting, fairly definitive paper really on herd immunity from Journal of the American Medical Association. Now just before we do this, I did read this. This is another, this reference here is a JAMA article that just teaches people about the principles of herd immunity, whereas this one is about herd immunity and COVID-19, this one specific. But this one here did mention that 60% alcohol kills the infection. So I just thought I'd bring that up because yesterday, the study we're looking at yesterday said the virus would be killed within 15 seconds in contact with 80% alcohol. Well, here we have confirmation that 60% alcohol will kill it as well, which is what we've always thought actually. So 80% works, 60% works. Just thought I'd throw that in for clarification from yesterday. I was just left thinking about it and I thought, well, better. Anyway, herd immunity. This is basically information from this article here. Click on it, read it. It's quite an accessible article actually, quite accessible. This is where people are given indirect protection or community immunity, where the community is immune because of the individuals, giving community protection, protection of susceptible individuals. So this is what herd immunity is doing. And this can be acquired in two ways. And of course, you probably know this. Herd immunity can be developed through people getting the active infection, developing immunity, therefore being immune, or by being vaccinated. And a large part of what this paper is arguing is that the natural approach, the herd immunity approach, probably won't work very well in COVID-19, is what it's showing. Now, it also talks about the herd immunity threshold. Now, by way of context, here we have some different conditions. Now, this is the percentage needed to get herd immunity, and this is the R value here. So what we see is conditions with high R value. For example, here we have measles. We need over 90% of people to be infected to get herd immunity. Other conditions, for example, poliomyelitis in Europe, 1955 to 1960, we needed about 84% to be infected because the R0 is about 6. But SARS coronavirus 2, it's looking at about 60% need to be infected because the R0 is working out to be about 2.5. And there we have different infections and their R values. You can look at that at leisure. There I am. Now, so this is the idea of herd immunity threshold. So the proportion of individuals in a population having acquired immunity that can no longer participate in the chain of infection. So how many people is required? This is the threshold for herd immunity. And if we reach the threshold, current outbreaks will extinguish and can go away, which is what we want, as SARS coronavirus type 1 went away. No longer exists in the wild, which is great, of course. Now, herd immunity threshold depends on the basic reproductive number. So if we go back to this diagram here, and we think about the herd immunity in SARS coronavirus 2, which is about 2.5, well, this one person here can come into contact with about 2.5 other people, therefore is unlikely to spread the infection here, because these people are immune. The I stands for immune here. But if the R naught is bigger, they could come into contact with, say, let's say they can come in contact with 8 people here, then I think you can see that can include a susceptible person. So basically what we're saying is the higher the R value, the more transmissible the disease, the higher percentage of people need to be immune for herd immunity to kick in. That is what we're saying. Lower R values, lower percentages needed for herd immunity to work and to kick in and have an effect. So, of course, that's exactly what we see on this diagram that we looked at already. Lower R values, lower. So that one there, for example, H1N1 influenza, South Africa study 2019, the R value there was about 1.25 and the herd immunity threshold was only 25%. So actually remarkably low. Zika was a bad, well, it didn't make people very sick, but it caused birth defects, Zika. 2015, 2016, South America. So the R value there, around just over 2, just over 50% required to establish herd immunity. So that's the way it's working. So herd immunity threshold depends on the basic reproductive number. So measles, which is a very high R value, 12 to 18, therefore over 90% of people need to be infected to establish herd immunity. But the R value for SARS coronavirus 2 so far has been between 2 and 3 in this pandemic. Now we know that the R value can be higher if people are living closely together. The R value will be lower if people are living further apart. If there's more social mixing, the R value will go up. So R value is not something that is determined by the virus, but it's of this value has emerged over the course of the pandemic so far, and this is roughly what it's been. So practically it's 2 to 3. And this paper tells us, as a result of that, the expected range for herd immunity is between 50 and 67% in the absence of any interventions. If human beings do nothing, this pandemic should stop between 50 and 67%, 50 and 67% of people being infected. So we've said around about 60% for some time, so that's not too far off. Now the duration of protection is a factor, because if people are only immune for a short period of time, obviously then they can become reinfected and go on to infect other people. If people are infected if people are immune for many years, then the herd immunity will last for much longer. And in coronaviruses, this is interesting. So we know that there's four coronaviruses that cause basically a common cold. And the immunity to these is very short-lived. It only seems to be a few months, sort of 6 months or so, probably at the most. So someone could be reinfected with the same virus a year later. Clearly concerning. But SARS coronavirus 1, people were last infected with that in 2003, and people that were infected with that in 2003 still have immunological memory T cells to that virus now, 17 years later. So SARS coronavirus 2, it seems to me from the data we have so far, is more like SARS coronavirus 2 rather than the common cold viruses. That's why I'm optimistic about long-term immunity. Do I know that for certain? Not yet. We don't know that for certain yet. Information is still coming in. So duration of protection is going to be very important. Duration of immune memory is a critical factor. This immunological memory. Does the immune system remember the virus? Will it still be immune to it? Determining population level protection and a sustainable herd immunity. So in order to determine this, to determine population level protection, we need to know more about the duration of protection. And at the moment, this is still a bit of an unknown. So measles, varicella, rubella, these have long-term immunities. Seasonal coronaviruses, they have short-term immunities. SARS coronavirus 1 is in this group. We could put that there. That has a long immune time. Immunity for decades rather than years. Pool of susceptible individual increases again if people lose their immunity. So someone could be susceptible, then become immune, then become susceptible again, if it turns out the duration of protection is short, but so far it's looking like it's not. Periodic vaccination can maintain herd immunity. So if it did turn out that people are only immune after vaccine for, say, 2 years to SARS coronavirus 2, we could probably cope with that because we could just revaccinate people every 2 years. Just like we have to get the influenza vaccine every year. Inconvenient, but keeps the infection down, and in the case of SARS coronavirus 2, I still believe can get rid of it. Now, another factor in herd immunity is what is called heterogeneity. Now, this is how it begins, and this is how hetero means different. Now, the R values normally assume that there is free mixing in a population, that all members of the population freely mix. But of course, we don't all mix with all members of the population. I tend to mix with my mates and not mix so much with other groupings. And we're all like that. And that can reduce the spread. Because clearly if I'm a hermit and I live in a cave up somewhere, I'm still a member of the population. But if I never see anyone, then I'm not going to get infected. So the mixing within a population is important. This is one reason that the virus has spread quite rapidly in young people over the summer, because they tend to mix very freely and widely to socially interact. So that's another factor. Now, the next factor the paper talks about is T-cell cross-reactivity. These T lymphocytes, so in other words, what this means is that if you're exposed to one coronavirus, you could have a level of immunity to another coronavirus. And again, this is not fully known. There's quite a few unknowns here, really. We have postulated that people in maybe parts of Asia and parts of Africa have had a very low infection fatality rate because they already have immunity to other circulating coronaviruses. Maybe even coronaviruses that haven't been identified by virology. That is quite possible. Or cross immunity from other infections, such as tuberculosis vaccines, such as parasitic intestinal worms, such as potentially malaria. So if that T-cell cross-reactivity is there, that's good, because it's going to give levels of immunity. So cross-reactivity with other coronaviruses may confer relative protection, probably not absolute protection, but a degree of protection, relative protection. It's less clear if that's sterilising immunity. It probably isn't. I think we can say it probably isn't, so we'll put a cross there. It's probably not sterilising immunity. So host could not carry or transmit infection if it was host infection, as opposed to reducing the severity of the illness. This is probably the more likely thing with T-cell cross-immunity. But again, the level to which it already exists is a bit unknown. We're not sure about that one. Infection-based herd immunity as policy. Now here we come on to more difficult areas. Now, we did talk about the Great Barrington Declaration recently on this video, and I have got a scientist and a very senior physician to talk to, hopefully soon, about who are supporting the Great Barrington Declaration. But let's see what this thinking on herd immunity will have to say about that. The bottom line there is it does tend to argue against the Great Barrington Declaration. Now, I'm not poo-pooing it. A lot of clever doctors and scientists are supporting it, but I'm not sure this gives any evidence for it, and I suspect it gives some evidence against it, actually. Infection-based herd immunity as government policy. So is this a good idea? So this would let low-risk groups become infected. Just leave them to it. Then sequestering or guarding susceptible groups, locking susceptible people away. This will give low infection fatality ratios in low risk groups. Low, but not none. So there would still be some risk to these groups. And basically, full guarding, is it possible? I mean, I think we'd have to say so far in the course of this pandemic, guarding has been a complete disaster because so many vulnerable people have been infected. Is it any better? Probably better than it was. It's still nowhere near where we would need it to be, though, to fully guard vulnerable people. And even the people that get infected to produce herd immunity in the low risk groups, there is still some risk. And of course, what we don't know at the moment either is the prevalence of long COVID, people with long-term sequelae as a result of this infection. Now, in the past, what's happened? Well, Zika in Brazil, Salvador in Brazil, the people there, enough people became immune through natural infection to generate herd immunity. So where is it? Zika, there we are. It's that one, the blue one. So just over 50% of people became infected, and herd immunity was established without vaccination. But this is unusual. This doesn't normally happen, actually. Zika is kind of, it's a bit of an exception that herd immunity has been reached without vaccination. The herd immunity has been reached through natural infection. It's not that Zika makes you particularly sick. The big risk is if you get it in pregnancy, and it causes these terrible cases with babies with microcephalic babies, babies with small heads, and consequent neurological problems and learning difficulties. Zika, of course, is named after the Zika forest in Africa somewhere, and I can't quite remember where it is. Ebola is named after the river Ebola, I think. But of course, SARS coronavirus 2, the World Health Organization decided not to use the name of the place it was first discovered, somewhat breaking with tradition for reasons of their own. Now, Sweden went for the herd immunity strategy. It never declared, but I think that's basically what they did up until about late March. And then they seemed to reverse their thinking in late March. So they kind of went for it for a while. And the seroprevalence in Stockholm reached about 8% by April 20. So 8% of people. Now, Stockholm was the epicenter in Sweden. So in rural Sweden, it would have been much lower. So that's despite going for this herd immunity strategy, we think, February up until late March. 8% of people infected. But then in Geneva and Barcelona, similar numbers became infected. So it didn't seem to make a lot of difference, really, going for this herd immunity strategy with 8% of people infected. And actually, places that weren't going for the herd immunity strategy, like London and New York, had higher infection rates than these. So nowhere near the number to establish herd immunity were infected in Stockholm. And as we say, the Swedish authorities have now gone back to a more traditional approach. They're not going for this herd immunity. I think the difference now in Sweden is they rely very much on the integrity of the individual to follow rules rather than dictating rules, and that does seem to be working with the reasonably compliant Swedish population. But as of that date from April, it wasn't making much difference, really, just 8% infected. So how would this herd immunity strategy work, for example, in the United States with 33 million people? World Health Organization say the infection fatality rate is about 0.5. We think it might be a little lower than that. But it would take 198 million people to become infected. Do the math yourself. Or as we say in the UK, do your maths yourself. And you're looking at pretty well 1 million people potentially dying before the threshold of 60% was reached. So the conclusions from this study. Infection-induced herd immunity is not realistic at this point. This is what they conclude, having considered all these factors, the things we know, and of course quite a few things we don't know, but this is the conclusion the team have come to. Vaccine programme must be efficient and broadly adopted. Now, what they're saying is that herd immunity has rarely been achieved through natural infection in the past. Zika's an exception. Normally it hasn't. Normally vaccination is needed. I mean, just think of the scourge of smallpox that was with humanity for thousands of years, tens of thousands of years, probably. Smallpox, the damage that did, and it was only eradicated with vaccine. It never reached a herd immunity situation in smallpox. So the team believe a vaccine is going to be necessary. Now, my question is, will the vaccine programme be efficient and broadly adopted and accepted in your country? In the UK, actually, I think it probably will be. In the United States, I'm not so sure. So that's kind of where we're at. So longer term, we're going to learn a lot about the way the virus works from these human challenge studies. We're not going to know that till next May, but we will learn a lot. These studies will also probably investigate what we call second generation vaccines that could be even more effective than the ones we're working on now. Again, meaning that herd immunity could be established by using much more effective vaccines. The studies that have got on herd immunity now indicate that herd immunity strategies are probably not going to work with SARS coronavirus 2. The virus will probably never go away. We're going to need vaccination to get rid of it. And I am unashamedly in the vaccine camp, because I've seen people with tetanus, I've seen people with polio, I've seen people with diphtheria, all common illnesses that we used to have. I've seen them in difficult areas, mostly in poor countries. They're horrendous diseases. They cause unimaginable human pain, suffering and death. And we don't see them in the UK. We don't see them, as far as I know, anywhere in the US because of the vaccination programme. And which vaccine gets there first? Well, that's going to be important in the short term. In the long term, I think we're going to have a variety of effective vaccines against SARS coronavirus 2. So I do believe that after a season or two, or probably three, SARS coronavirus 2 will go away, which of course is encouraging. Okay, that's a bit of a long video, that. I hope we managed to get through it, but lots of interesting principles there on infection, viral dose, immunity, vaccination, and this important concept of herd immunity. And I would say, I think the herd immunity information we've looked at here argues against the Great Barrington Declaration allowing people to develop natural herd immunity. The history of infectious disease seems to be arguing against that at the moment, but I am going to accept counter-argument fairly soon, but it's going to take quite a lot to change my mind on that. Okay, thanks for watching as always.